All right. Thanks so much for the kind introduction. How much time do we have here for my presentation? 42. All right. All right. It's my great pleasure and indeed an honor to be here today to share some of the research, the results. So my name is Chan-Byoung Chae from the Yonsei University. I am also a visiting professor at UC San Diego, collaborating with Robert Hayes and Nuria Gonzalez-Prelkic. So today we have the really wonderful talks, but my presentation, I want to have the something a little bit more futuristic technologies for the next generation the wireless communication. More specifically, I want to introduce the molecular MIMO and magnetic MIMO. These technologies might not be the something we can see in the market or in our area anytime soon, but I believe they are certainly the worth they're considering. So, all right, so I just prepared the one slide to take a short moment to introduce myself. Again, I am the professor at Yonsei University, and prior to this, I worked at Bell Labs in New Jersey, Murray Hill, focusing on the massive MIMO and small cell networks, more specifically in what is known as at that time light radio, and or formerly the SNAP systems. And I also completed my postdoc fellowship at Harvard University, and after earning my PhD from the Robert Hayes, from the UT Austin, he is now here eating something. Anyway, it's wonderful to have my presentation in front of my advisor. So before the PhD, I spent nearly 5 years at Samsung Electronics as well, working in the advanced research lab. So during that time, I had the opportunity to contribute to the WiMAX and 3GPP standards, mainly on MIMO and physical layer solutions. And we proposed the over 50 technical contributions, and I believe the 15 of the patents were adopted in the 3GPP. So when I first started my professor life at Yonsei University back in 2011, I was figuring out what I really wanted to do in my academic career. So I had to choose between taking just the signal processing research I did at Bell Labs and Harvard and UT Austin, or trying something new and more impactful stuff. Even I had the phone call with Robert to ask his opinion. But after some thoughts, I decided to dive into two new exciting the projects that are the wireless prototypes and molecular communications. So there's the quite famous old Korean saying that says, the singing once is better than hearing the 100 times. 백문이 불여일견 in Korean. So it means the singing something for yourself is much better than asking about it the 100 times. So I've tried to distinguish myself by focusing on the prototyping, the research. The one area I'd worked on was the full duplex radio. I'm sure you already quite familiar with that idea, but my team showed the working system at IEEE GlobalCom in 2014. We kept improving it, and we presented new ideas every year, every December till 2019, and before we had the COVID. And we restarted our demonstration the last year. And we got some good award for our hard work, like the CS Innovation Award and WCN Best Demo Awards. And I also took a big risk just by looking into something totally weird stuff, the molecular communication, which was the very new and pretty wild idea at that time. So we learned a lot from just reading the textbook, biology, chemistry, and we built the prototypes of the real system at different sizes, at macro scale, mesoscale, and nanoscale. So for this contribution, we also got several best demo awards from IEEE InfoCup and IEEE ICC. So for the past 14 years, we've been working really hard. And thanks to our great partners like Samsung and other companies, And we've been able to showcase some really cool technology. I can't cover every topic here today, but here you have some highlights. As I mentioned first, we were one of the very first teams to demonstrate the real-time full duplex radios. This technology is now being considered in the switch PP standard in the release 19 and 20, of course, with a different name. And also we kind of tackle the very severe path loss issues in millimeter wave spectrum just by designing like the millimeter wave lens MIMO. And also to make the more like the immersive experiences, we implemented wireless VR and haptic platform. And also for the 6G NTN, we demonstrated free space optics MIMO, FSM MIMO. And also recently, we showed the smart communications for the 6G AR. And plus, we proposed like some the applications for 6G or B60, like molecular MIMO and magnetic MIMO, and which are the main part and main topic of my presentation today. So I don't think we have enough time to review every details. So I prepared a quite short video clip on my group's the research activities. Doesn't work. Just one sec. Are we gonna have any? All right, this is my office. And all right, so now to have the background music. So this is like the very first full duplex size of MIMO, and we showcased the network full duplex and also open map-based flexible duplex and haptic devices and millimeter wave lens and multi-user full duplex, and also wireless haptic at Mobile World Congress in Spain, and lens MIMO, wireless haptic, free space optics MIMO, and also these are the equipment and our platforms. So we spent quite some time to have the modem chip for the 5G and R as well. And this is like the millimeter wave, the MIMO demonstration, and it's a real-time system. And also we were kind of the very first group to use the ray tracing for having system level evaluation. This is the Yonsei University building. We started using that one in 2009 when I worked at Bell Labs. And of course, we also have the platform as the NVIDIA using. And also if you just move to the different part, that's our robot arm and haptic glove to capture the motion information. And this is the demonstration for the kind of the remote surgery, the applications. And this is quite popular and big. Must full duplex the platform. And we achieved almost 120 dB cancellations for the 3.5 gigahertz. And we did the demonstration last year, December, for the upper midband as well. And this is the millimeter wave, the IAB demonstration. So, and we have the full the videos of each technology, and this is the one for reconfigurable intelligent service. But let's have something, and then we show the feasibility of our passive, the almost zero power, the transparent reflector, and everything. But I don't think we have enough time, so I'm gonna skip. But don't worry, we actually have the YouTube channel where all the demonstrations are available. The only downside is that I currently have only 164 subscribers. So please be the 165th, 166th. So you can find our YouTube channel on YouTube by searching the two keywords. My last name is CHAE and YONSEI. I really appreciate your subscriptions in advance. Can I have 1 minute to wait? All right, so let's get started with my main part by sharing one of my favorite parts. Every great movement must experience 3 stages. ridicule, discussion, and adoption. When he started this research, like a molecular MIMO or the magnetic MIMO, nobody believed the system would work. And even now, there are some still doubts about our system, but it's getting better and better. And I believe we're still in the early stage, somewhere between ridicule and discussion. I know that our work would not be the great movement, but we hope it will be an important step for science and engineering. And let's think about different kind of communications. Imagine the Internet of nanobio things. Suppose we implant two tiny nanomachines, one above and one below the heart. These machines they communicate each other to check the heart condition. And for this application, we don't need to achieve the 1 gigabit per second data rate. Just 1 bit per minute or 1 bit per hour, it might be enough. So in this case, can we still use the conventional RF technology? Because if you look at the blood vessel, and typically we have the 10 nanometer wide. So the conventional, the RF technology might not work pretty well. And also the nanomachines, it should have the better biocompatibility than our conventional RF systems. And also, the nanocommunications, we have the relatively short range. So we need some kind of the complicated relay networks. So just by passing through the multi-hub relay networks, eventually we might have some alert message on our galaxy. Oh, I just detected quite abnormal some condition, so you should go see a doctor or something like that. So this could be one huge case of the molecular communications. But however, it doesn't always have to be the nanoscale. For example, for the military applications, and we might need a very special way to have to keep the communications very secure. So for example, those kind of the applications, we could use this kind of the different the communication paradigm. So for this, so we need to revisit with size 7 layer. In addition to the conventional direct layer below the layer 1 basic layer, sometimes we call that layer 0. I guess we could also consider the biological layer to support the emerging the biohealth and e-health applications. So this is kind of I believe, the revolutionary changes. With the evolution of the communication media from wires, we used to have the wire, right? Copper or telephone line or whatever, to the wires to wireless, and also most recently to liquid-based the media, like some pipeline or blood vessel and other applications. So we need the truly groundbreaking application for the 6G or B6 or 7G. And I believe this e-health or like the bio health, this area could be a good candidate. So we could combine with the legacy technologies. So, all right, again, the singing is believing. I like that quote as well. And let's watch a brief demo video. The molecular communication and tabletop test bed. So here, we want to deliver the 6 alphabets YONSEI without having any RF modules. And so we spent almost the $50 to have this test bed. We had the fan and electrically controllable spray. And at the receiver side, we had the really cheap chemical sensor, which was the MQ3, just for the alcohol detector for the test bed. Even that the fan was not made by Yonsei University. We just print out the Yonsei logo and just put on the very cheap, the $1 the fan. But finally, we delivered the message, and at the receiver port, here we successfully delivered the 6 alphabets without any advanced Arab technology.
You did the cups of alcohol?
Yeah, right. 99% isopropyl alcohol was quite dangerous. So we had the one experiment, and then we opened the windows for 30 minutes to have more air, fresh air. So anyway, yeah, we did that one. We did that one to show, I mean, our story is not just a story. We could have something, the real working system.
So the real system will be films and I mean, chaotic.
Right.
So
The
fan was able to monitor, so create a channel.
Right. So to have the drift velocity, otherwise we should rely on pure diffusion mechanism, which means sometimes it would take a really long time.
So the fan was pushing on.
Yes.
That like the drift velocity. So like what our heart is doing, like the pumping or something like that. Oh, that's a good question. And then I have something to answer your question.
Out.
Right. The Sandy is fine. I mean, after our experiment. Otherwise, if you just have some spark, and it's gonna be right. You know, I tell you quite the funny story because we wanted to have the AI based channel the estimator. So for that, we had to have a really huge data set to learn, and we used that test bed to collect the channel responses. So it took almost 2 months because we had to be very safe.
And why do you insist that it needs to be chemical? Because this is like a chemical, not biological. You are not sending cells. You are sending, alcohol molecules, basically.
Yeah, messenger molecule.
Why not, for example, making smoke and a camera and then having puffs of smoke? That's what we did.
That's what we did a long time ago, 500 years ago, the Joseon Dynasty.
I mean, yeah, everybody did that. And that
Right.
was also very successful.
Yeah, right. But the thing is that this is like the very early stage, and this is like the a very simple tabletop test bed for free space channel. But eventually, we want to go inside in our human body. That's the thing. Right. So I'll have the more slide. And so, for these applications, if you just want to look inside our human body, then we have to have the nano robots. And this is what we call nano networks, nano communication networks. So what exactly the nano communication network is? I mean, it's a system, that connects the multiple nanoscale machines. They work together for some simple or sometimes complex tests, like health monitoring or target drug delivery or the other applications. And for that, of course, we could have the electromagnetic stuff as well. But in that case, we need a few hundred terahertz maybe. So I'm not quite sure if we could penetrate like the single blood membrane or something like that. And other option is the eventually chemical-based approach. So this is like the one simple animation, purely based on diffusion mechanism. And we compare the differences between the electromagnetic communications and molecular communications. For the molecular communications, of course, we do not have the light speed. It's extremely slow. If I just have my perfume right now, and then after maybe 1 minute, the Dongwon might recognize that scent because we need some time to wait until some molecules are moving around on the Dongwon, right? So here heavily depends on the diffusion and drift speed and we have the different noise characteristics and different information and different applications as well. So we're not arguing we have to replace with the conventional 5G or 6G networks with that idea. Rather, we have some specific applications. I believe we could use those kind of the methods. So, I mean, I mentioned the diffusion equation several times, but since we're given just the 30 to 40 minutes, I'm gonna skip all the mathematical details, but we all learned about diffusion equation or heat transfer equations during our undergrad studies. So one difference is that here for communication, we care about the first passage time density, meaning the probability that a particle first reached a destination at time t. So after just considering the probability and using some approximations, so we finally have the function called inverse Gaussian distribution. So for this distribution, we fix the distance meaning the communication distance between the transmitter and receiver. And we care about the arrival time. We used to have something the other way, I mean, the different one setup. So for the conventional, diffusion the equation, we fix the time t, and we care about the distance. Yeah, that's why we have the time inverse. And this is like the some closed form expressions for the 1D space. And this is the big main contribution by the Albert Einstein. In his PhD dissertation, he derived that equation using Markov chain. So after that, we generalized his approach to have the more generous concept.
What's D in it?
D is the diffusion coefficient. XC is like clip the location, meaning any positions we observe how many molecules we have from the transmitter at the time t. All right, so let's talk about communication part. Then we can skip that one. These are the background. Of course, we can use the wireless, the nanomolecular communication as well, and wired one as well, using the active transport. And also, we could have the carbon nanotube or graphene to have the small nanoscale machines. And here, just want to have the three important key questions for our discussion. First, what is the theoretical limit? And what kind of the solution can you achieve that limit? Those are the very fundamental questions. And we need to we need to establish the channel model, because we do not have the Rayson channel, we do not have the Rayleigh fading channel or SCCM channel or whatever for molecular communication, because we have the totally different environment. And also we have to work on energy model, because we do not have the SNR definition, we do not have the transmission power, we don't have the something important factor in dBm or dB. So we don't have the SNR either. So we have to define some good energy model as well. And also we should understand the channel capacity, like what we did for the AWGN channel, like the channel is log to 1 plus SNR, and how much information can we deliver with no errors under the certain practical circumstances. And also we should design the practical modulation and demodulation techniques, and also error correction codes. We don't have to use LDPC or polar codes for molecular communications, because this is too tiny robots. We do not have any huge energy for even computations. And also, since we have the only pure diffusion mechanism, we do have the very severe intersymbol interference. And then we cannot use the WebDAM here. So we also need to work on ISI mitigation techniques, and also to increase the data rates. And we need the somewhat advanced technologies, like what we have for the wireless communications and MIMO. And that's why we apply the MIMO for these molecular communications.
Immune system is adaptive, right?
Oh,
Your
where-
ability
Sorry, just 1 second. Oh, where's that? Sorry?
The immune system is adaptive.
Yeah, right.
So you may be fighting a battle against the immune system, trying to get rid of all the this one molecule that's to make it be, maybe.
Immune system will kill it.
Yeah,
Yeah,
right.
but one thing is, if you use it to work, or in order, you need to have a concentration above standard. I mean, that's why, like, if you put a skunk in the room, you smell it. Because
Sure,
it has a
sure.
certain molecule above the standard.
Sure.
So where are you gonna get these molecules? Are you gonna have like a little reservoir or something, or are you gonna make them in situ? Because you cannot use the background type of molecule. Like
That's
sugar
true,
and protein
that's true.
And this and that, because
Yeah, that's true.
yeah,
That's
they will
why
use
I have
that
the
in all-
yeah. That's why I have this line. So this is the one example of the messenger molecule. Of course, we have to generate something. Otherwise, there's no point. I mean, it's not really straightforward to distinguish between the messenger molecules or just background the molecules. So this is the one example as the modulation. So we propose using isomer-based the modulation techniques. The isomer in chemistry, isomers are the molecule with the identical molecular formula with a different just structure in space. So if you look at the second one, we exactly have the same the number of the atoms, but we have just the different locations for OH and OH. So this is distinguishable at the receiver side. And then we have exactly the same diffusion coefficient. And this is the one possible candidate we can use as a messenger molecules. However, I fully understand and agree. If you just look inside our human body, we have to find really safe messenger molecules that does not have any negative effect inside our human body. So there's a totally different story. And maybe some biology people, they work on those kind of problem. But this is the one just a concept as a communication engineer.
Where do we get them from? I mean, let's say, do we store them? Do you have like?
No, I mean, if you look at the figure right side, this is the one example of the eukaryotic cell. So we can also generate the certain types of the molecules in the nanomachines.
Somehow your biomechanism generate in some way.
But
You do that, yeah.
the body typically does generate molecules that it does not need.
Yeah.
Yeah.
Synthetic biology. Like Russian biology.
Yeah, but
You can construct anything that you want.
you can, of course, outside, but can you ask yourselves to do that?
Yes.
Yeah.
you can
That's the
engineer-
what contribution I think the people from Northwestern University who got the Nobel Prize in chemistry in 2019 or something, their contribution was about that real nanomachines. It's quite far from our engineering perspective, but still, I mean, I told you this is quite early stage, so I don't have the good answer for those kind of really good questions yet. But this is the one just the example to understand the mechanism or fundamentals of the diffusive communication. So here is a question, preliminary result, and that's the one example we used for one of the JSAC paper. We propose using hexosys 66H12O6, mainly because it has 32 different levels, meaning we could have the 5 bits the modulation order just using the hexosys. And again, we can also achieve on-off or like the shift king. like what we use for optical communications. And we achieved a impulse like the chemical emission or square light emission, not have the really peak number of the emissions. So, and also, of course, we could have the multiple levels to achieve the higher order modulation. And also, these are the concentration-based modulation we filed. And also, we could apply cosine waveform with the different frequency. So these are just very simple, straightforward modulation method for the molecular communications. And also, we analyze the channel characteristics because this understanding channel part is most important for communications, and we compare them with the electromagnetic channel. So this is quite the theoretical contribution, but in the physics domain, after Albert Einstein dissertation, the diffusion characteristics for a point transmitter and point receiver, it has been well investigated. That's what the Einstein solved in his dissertation in 1905 or something. But for a little bit more general setup, like the sphere to sphere, or even for point to sphere, and they have remained this open problem. So we have solved the really very special case with some ideal assumptions on the receiver side. And based on our findings, and we investigated the channel characteristics, such as like the propagation delay here, and also path loss. So even for free space diffusive channel, free space channel, for example, like the path loss is proportional to 1/d square for electromagnetic waves, but it becomes 1/d⁻³ for molecular communication. The different characteristics, which means we need different approaches for the communications. Any question?
Why is it 1/d?
Well, in that, we are not looking into the power concept here. That's why we have the 1/d². But if you just look at the molecule itself wise, it decays with the 1/d. But if you look at the peak, the position for the inverse Gaussian distribution, and then from our channel, the characteristics, and we got 1/d⁻³, meaning we need more relays to secure reliable long-range communications.
Volume as opposed to.
Right. This is the 4-point to sphere. So we try to solve the sphere to sphere, but still we don't have any good approach for that system setup. So the second question, the first question, all right, we design or we propose some theory, and we try to understand the foundations of the random movement or molecular communications. But so one might argue that just a theory is a theory, and we need to ask this question: can we really deliver information through the molecules? Just as we have done with our technologies for 3G, 4G, 5G, whatever, we also need to measure the channel responses to validate the channel model we got from the theoretical, the point of view. And also we need to design and model with non-ideal transmitters and receivers, because we have the chemistry. So this is totally different from photon or phonon. It doesn't disappear immediately after we use for signal detection, right? So
it's there.
still there.
And it has an exponential
Right.
as the concentration goes down.
Right.
It's there for a long time.
Right. So especially the sensor we used for our test bed, we used NQ3, like maybe $1 or $2 for that sensor. It has really slow turnover rate. Sometimes we need 5 seconds to get recovered to detect the second symbol. That's why we have the so severe ISI, or sometimes we have the non-negligible gap between theoretical curve and measurement curve. But anyhow, we need to use that practical component. That's why we modify the channel model just by considering the practical imperfect features. But both actually. Because when we started this work, we searched a lot to find some good chemical sensor. But mostly it was for toxic gases. That's why we bought very cheap chemical and alcohol sensor that the policeman uses in South Korea for the 음주운전 단속.
I call it like a drunken driver.
Right.
So what's the problem you are seeing?
Here, I mean, first, we want to understand how it works and how we should design the communication systems for our applications.
For interbody,
Eventually, interbody area network. And at that time, even we didn't have any well-known channel model. We never had good practical structures like a modulator or channel codec or any good solutions mitigate in the symbol interference or whatever. So we first spend some time to fill that blank in the communication systems.
I mean, you're giving me great ideas. For example, I want to communicate with JP, for example, and in a completely covered way. So maybe I should have a device that controls a little bit my sweat gland. And, I just do little puffs of sweat, that I can modulate very little. And he has a sensor that is tuned to my sweat, to my DNA sweat.
Sure.
And then we can communicate basically like this, even though it's very slow. You can send him
Sure.
a very slow message by sending him, this is what I think, and in a meeting, and nobody can hear the message that I'm sending him.
Sure.
Or something like that. I mean,
That's
it doesn't need to be inside, but it can
Sure,
be also
sure.
outside, as long as it is chemical-based and diffusion.
Right. That's
So
the
one form of body.
intra-body. Sure. I mean, that's a good for secure communications because nobody can detect what's going here. I can smell something, but I don't know what's going here, for example. So that's why the military people want to have something very weird, the communication protocol for their own purposes.
But it's very slow. That's the whole
Yep.
thing.
Yep.
It's very slow.
All right.
But now I get that. At least your
Uh-huh.
Are you also trying some a little more complex biases and still the human body? Are you covering some of them?
Good question. Next slide.
Okay.
So here, I spent some time to investigate the channel parameter. And this is the one, we have the huge gap between the red curve, the representing this radical one, red curve represent the measurement and result, and blue dotted lines indicates the theoretical results. We have totally different results. That's because of our imperfect the transmitter receiver the structures. So we modify the channel equations to consider this imperfectness. And our first demo, many people ask about the data rate because I never mentioned the data rate in that video clip. And 1 bit per second. And sure, there's a bit because of the speed of the fan. If you just increase that your fan speed, and then we could achieve the higher, data rate, but it doesn't necessarily to be proportional because of the chemical reactions and the receiver part. So here, well, here, yeah, right.
The detector is slow, but you could pay more money and get a better detector.
Well, I had at least $1,000, but I wasn't able to find the better the chemical detector, except the toxic gases. Anyway, I got that question, and you know the 1 bit per second might be enough for in-body area networks, but we wanted to go further. So I mean, I was a student of Robert, and I was the also MIMO man. So I applied MIMO technology to this problem, and this is the second demo system. Still have the echo.
As sly as a fox, as strong as an ox.
What about that? And still we have. So here we have the one transmitter because I have the mic here. Oh no, let me try. So it was the 0.29 bit per second because at that time we had the longer the distance between transmitter receiver, but by having multiple transmitter and multiple receiver and here, of course, we could also control the distance between those two transmit nodules to test the more correlated diffusive channel or uncorrelated diffusive channel. And we also try to deliver the same text message, YONSEI, using to the MIMO setup. And this looked a little bit ugly, but I love that guy. I mean, we spent really long time to have that test bed in my lab. So here you could see the some emission, right? Yeah, molecular MIMO. Molecular MIMO meaning multiple transmitter and multiple receiver. But the thing is that we have the almost zero coherent time. I mean, we cannot use any instantaneous channel state information at the receiver side. So we have to rely on the statistical property of the MIMO channel. That's why we only achieve 1.7 times higher data rate compared to SISO. We were not able to achieve double because of the some uncertainty. So that is the molecular MIMO communication test bed. And after this one, we got more feedback because you know the first setup, the SISO setup, used the free space diffusive channel, and which are very different from the conditions in our human blood vessel. In the body, there are 3 types of the blood vessels. Arteries is about up to the 10 millimeter wide, and veins, the 8 to 100 micrometer wide, and capillaries, 5 to 10 micrometer wide. So for these conditions, and we created the new transmission method and designed a new test bed. Here, like what Gert asked before, of course, we have to think about Reynolds number to see the turbulence or lamina, or even for the lamina, we could have the uniform, or we could have the Poisson non-uniform the velocity. So we also analyzed everything. I studied a lot about the fluid dynamics. And this is the mesoscale, like in this cell, the molecular MIMO communication test bed. So here, the test bed consists of the 4 pumps that generate flow within the tube channel and also emits the messenger molecules. And this is system that we used bases and acid as a messenger molecule, and also those emitted molecules pass through the 2x2 the MUT channel, consisting of the junction and also the silicon tubes. And receiver detects the changes in the pH value, and we convert them into the electrical signal, and then we decoded that information. And this is like this one, sure, because we have the tube and also pumping.
Say, oh my God.
I like the background music. So,
When you're done,
so 2x2 MIMO. And yeah, we got the message. Here, this time, WCNC, name of the conference. All right, so I mean the final question here. So we we observe the same phenomena at the nanoscale because we used to have the macro scale or mesoscale test bed just for verify the concept. But to explore this question, we also designed the fabricated the nanostructures with the large surface area. This is in work with the one of our department colleague who designed and fabricated the real nano devices. And we can skip that one. So this is the system we implemented. Although, I mean, we could still improve this system, but what's truly remarkable is that the nanoscale detector sensor here was the specifically designed for the molecular communication task. It's small enough. It's like a few nanometer size, and I think it's the safe to be implanted near the skin, and we achieve the here 1 bit per second or 0.33 bit per second with a different target BER numbers. And this is the final demonstrations for the molecular communications. The transmitter part is not the nanoscale, but the receiver size, the receiver part. Indeed, we designed and fabricated indium gallium zinc oxide based glucose detector. And we measure the concentration or the signal detection, and we got HTACH, 5 alphabet. We delivered HTECH, but we got some error, and then that's why we also applied several the AI-based the detector because we have nothing, we have no knowledge about the channel, the conditions. So we also use the ML solutions for designing the ML, the signal detection. And also, this is the end of my first part, and I have the second part, but I think we have the only 5 minute maximum. So I will quickly go over the second part, the magnetic communications. The reason I have the gray color here is that still we cannot say it's communications. It's like the stimulation or sensing. That's right. So here, this is the magnetic MIMO. I mean, we propose the molecular communications, particularly for in-body area network, but it's not straightforward to apply that concept to the brain, where we have the CPU and the real important stuff. So as you might know, our brain has the quite different areas, and Broca areas, Wernicke areas, and DLPFC or PSAC, and each part has a different functions. For example, for the Broca area, and it is related to like the expression and production of speech. And also for the Wernicke is about comprehension rather than expression or something like that. So we thought we could enhance kind of cognition ability or conversation ability just by stimulating certain part of our brain. So you know the Elon Musk, they found a company named the Neuralink. They also have the similar approach, but they have invasive some chip. So we have to open our brain. So I really don't like to have that experiment in my lab. That's why we have the something beamforming technology instead of the opening our brain directly. So this is the beamforming again for brain communications. So here by applying, here we have the single coil here and multiple coils. Just by having multiple coils and also just by having some good approach, we could also maximize the directional gain for a certain target point. It looks like omni radiation pattern, and with the array, we achieve the quite a sharp radiation pattern. but we can still have the similar one using coil, Cooper coil. And also we could also steer the magnetic field a little bit, plus minus 5 to 10 degree. But here we don't have any phase concept. We don't have any phase shifter. We don't have any attenuator. So we only change the input voltage to generate some steered pattern. And this is our prototype. And we showcase the IEEE ICC 2022 and also CES 2023. And we now have the clinical trial with the several general hospital for like a brain disease, like a brain treatment, like Alzheimer treatment, and also depression or something like that. And also, all right, this is the really last one. So here, so we have the mechanical steering and also electrical steering using our optimized module. And when we move around, and that's the transmitter part is moving together, and this is the one, like the magnetic field forming to a certain direction. So right. Oh, it's almost the 55 minutes already. So let me conclude my talk. So here, what happened after the research, it will be just the funny story or maybe new beginning. So once we have some fundamental IPRs and macro scale, nanoscale, and mesoscale verifications, we will have the technology that will change the world. And I believe it will be crucial for the success of the 6G or even beyond 6G and 7G. So that's everything that I prepared today. And thanks so much for your kind attention. And also I will share my slides, and these are my publications on only molecular and magnetic stuff. And that's it. And also, please let me know if you have any chance to visit the Seoul. I would love to host your visit at Yonsei University. This is the main building of the university. And anytime, just let me know. I can have some special events for the visitors. Thank you so much. And